I'm going to tell you about our work on usable access control for shared distributed data. And this is joint work with my colleagues at Carnegie Mellon and also UNC Chapel Hill. So in today's world, with so much digital data percolating everywhere, access control is important but also hard. So here are some examples of things that can happen when access control goes wrong. This is an example of a girl who attempted to invite people to her birthday party using Facebook and accidentally set the invitation to public. 3,000 people showed up, they set some things on fire, the police had to come and break it up. It turned into a riot. It was not a good scene. There's also just endless amounts of reporting on how you can not get into college or not get a job as a result of things that you publish online in various mediums. And this might be possibly my favorite. Someone took their cell phone to work, plugged it into a computer at work to charge it. It turns out the network was set up to treat that as an external hard drive and immediately make that available over the network file system. The boss located some nude photos that lived on that phone, printed them out, made photocopies, and hung them up around the office. Ouch. So what all of these examples demonstrate, really, and many, many more where those came from, is that the traditional physical and social boundaries for access control are really failing. When you're inviting people to your birthday party using paper invitations, or when you're keeping your nude photos hopefully in a drawer at your house, there's much less likely that these kinds of problems are going to happen. We also know from lots of research that configuring access control properly is really difficult, even for experts and system administrators who get paid to do this. And in fact, what we've created here is a world in which all of us, our grandmothers, our younger brothers, are basically all our own access control administrators. And we also know that access control is basically a secondary task. No one signs on to their computer in the morning and says, I'm going to set up my access control policy today. And as a result, this is a task that users don't want to spend a lot of time on, especially since the consequences are sort of nebulous and in the future, and you don't really know what kinds of bad things might happen. So there's a lot of prior work, especially in the HCI literature, talking about what people really need in terms of access control for their personal data. And a few of the things that we know people need are, we know they need flexible policy primitives. And here are just a couple of examples of the types of policy that people might want to implement. So this came out of a user study that I and my colleagues worked on. And this is an example of someone who wants to share photos of the children that she works with in a community organization, but only if their parents agree that it's okay. Similarly, we know that things like location and presence can impact people's ideal access control policy. So we have things like, I would feel less embarrassed if I knew that someone 100 miles away was looking at it rather than someone sitting on the bus with me. And similarly, we also have some pretty fine-grained distinctions in types of content. Like one user who told us that some friends were allowed to see drunk photos, but not very drunk photos. So this is a subtle but apparently important difference. So we also know some other things that users need. We know that they really need the underlying security mechanisms to be principled rather than ad hoc, because as we all know, when you try to add security on afterwards, you tend to run into problems. And we've learned that semantic policies are an interesting building block for this type of thing, basically allowing users to describe the content in the way that they want and to organize the content the way that they want to help them make policy about it. And for purposes of this talk, I'll just use tags as a stand-in for this kind of semantic idea. And we also know that sometimes it's important for these tags to be private. So maybe my favorite example of this is John McAfee, who got caught running around South America hiding from the authorities because the geotagging data in some photos that were posted of him had not been stripped from the photos. And so the actual content of the photos was not sensitive, but the metadata, the geotagging data was. So we know that sometimes tags and descriptions of content need to be private. So what I'm going to talk about in this talk is our design for Penumbra, which is a more usable file system, a more usable access control design for file systems. And it rests on a couple of key building blocks, which I'll explain in more detail as we go through the talk. We have tag-based policy specification. We have, that should say logic-based and not log-based. That's kind of exciting. Logic-based policy enforcement. And based on these principles, we've built a prototype distributed file system. I'm also going to talk about some realistic case studies that we designed. So it turns out that evaluating this kind of system can be difficult for a lot of reasons. And so we put together these case studies drawn from real user studies that we've done, which provide benchmarks for the types of policy that we're talking about. And hopefully these benchmarks can potentially be reused by other people working in the same space. And then finally, I'll tell you a little bit about the performance evaluation that we did, where we found that this prototype system is sufficiently reasonable performance for the interactive use cases that we target. Okay, so I mentioned the key building blocks in Penumbra. The first is tag-based policy specification. And the idea here is just that we're going to allow users to group and categorize their content according to these descriptive or semantic tags. And these can be tags that are created by the user, or they can be tags that are automatically generated using, for example, facial recognition in photos. We're also going to use logic-based policy enforcement. This is an idea with a long history in the access control literature. The idea here is that we only want to allow access if a logical proof that that access is allowed by policy can be shown. And we like this for several reasons. It allows the kind of fine-grained and flexible policy that we know users are looking for. It provides a high assurance of correctness and allows us to have a meaningful audit trail, because you don't just keep track of who accessed what when, but you also keep track by keeping track of the proof of why that access happened, or which pieces of the policy allowed that access to go forward. So our high-level approach here is sort of as follows. So this is Bob, and he's using this tablet. And over here we have Alice, who has a desktop computer that has some of her photos on it. And so, for example, this photo of Alice surfing. And this also contains some tags and other metadata about Alice's content. So for example, this is a tag in which Alice says that this particular photo belongs to the Hawaii album. And we also have in this system some policy created by Alice. And so in this case, Alice has made policy that Bob can read or look at any files from the Hawaii album. And in our system, all of these policy credentials are cryptographically signed to make sure that they can't be forged or spoofed. So when Bob wants to access Alice's photo remotely, his agent on the system will create a credential which says Bob cryptographically signs that he's the person trying to access this file now. And so basically what Bob's agent is going to be able to do is to combine these three pieces of information: the fact that Bob is trying to do this access, the fact that this photo belongs to the Hawaii album, and the fact that Bob is allowed to read things from the Hawaii album, and make a logical proof that this access should go forward. And once this proof has been verified, then the file will be allowed to be accessed by Bob. So to come down just one more level and look at this in a little bit more detail, this is what the system looks like. So here on the tablet, we have an object store, which consists of a flat namespace for files, as well as all the tags that are stored in a database. We also have on the tablet a reference monitor, whose job is to guard access to all of the content that lives on the tablet and to verify proofs that access is allowed. And we have Bob's user agent, which is responsible for constructing these proofs of access to get access to this content. And over here on the desktop, and in fact on any other device participating in the system, we have the same general architecture. And we actually have not just one user agent, but potentially a series of agents, one for each user who typically uses this device. And on top of that, we actually have on each device a device agent, and these are used for remote proofs. So these are used to demonstrate from one device to another that it's okay to submit this content over the network to that remote device. So I think this will make more sense if we walk through an example. So here's how this works. When Bob tries to open this photo, it creates a system call to open the surfing photo. The reference monitor will intercept that system call and create a challenge. And it will send that challenge to Bob's user agent and say, prove that you can have access to this photo. Bob's agent will construct such a proof and send it back to the reference monitor to be verified. Assuming that the proof is valid and is verified correctly, the reference monitor will then allow the access to go forward, and it will look in the object store for that photo. Of course, as we know from previously, this photo doesn't live on the tablet, it lives on the desktop. So what happens at this point is that the tablet will go ahead and ask the desktop to open up that file. And so at this point, the reference monitor on the desktop, which is guarding access to this content, will issue a challenge back to the tablet and to prove that the tablet is a trusted or authorized device. And once it does that, it submits a backup proof, which the desktop's reference monitor will verify. At that point, the access will be allowed to go through, and the photo can be opened by Bob on the tablet. To get into just a little bit more detail of how this tag-based policy specification works. So here's this photo. It has type equals photo and album equals Hawaii. Alice lets Bob view such files and doesn't, for example, let Bob view her tax spreadsheets. And so the idea here is that we want to minimize the mismatch between the intended policy, what the user thought of, and the actual specified policy. This aligns closely with users' mental models and allows this policy to propagate across groups of files. And we've previously conducted a user study which supports the idea that this approach is really feasible. So in a system like this, tag design becomes really critical. First of all, the tags have to be authoritative. Policy depends on them. And so if Bob can somehow change that tax spreadsheet to look like it's a Hawaii photo, he would be able to get access to it in contravention of policy. We also know that tags may need to be private, so I gave an example of that earlier, that access to content is not the same thing as access to tags. And then finally, we know that tags can potentially be conflicting. Two people may describe the same content differently. And so you might think that this is, for example, a cute photo and want to share it with everyone, whereas I might have tagged it bad hair day and not want to show it to anybody. So in order to meet these requirements, how do we design these tags? Well, we do a couple of things. First, we treat all the tags as first-class objects. So access to a tag has to be proven independently of access to the content that it describes. And secondly, all of our tags are in fact cryptographically signed credentials. This has the nice property that two people can describe the content differently. And it's clear that Alice, for example, puts the surfing photo in the Hawaii album, whereas perhaps Bob thinks it's embarrassing and wants to put it in an album he's keeping for blackmail or for making fun of Alice later. And this also allows these tags to be unforgeable, so that when we make policy about them, we know that it's correct. So what this really means is that sometimes in order to have access to a file, you first have to make a proof of access to metadata about it. So let's take another look at this example. So in this example, first Alice signs that Bob is allowed to find out the album tag for any file. And if that's the case, Bob can try to read the album tag for this particular file that he's trying to open and make a proof that he's able to do that. And this will allow Bob to have access to the information that this photo is in the Hawaii album. And then he'll be able to use that as part of the proof example that we went through earlier to complete a proof that he's able to actually open the file itself. So one of the interesting design points that we had to make for this system was how to correctly map system calls to challenges. So of course, system calls don't exactly map necessarily to the higher level user operations that people are thinking of when they set up their policy. And so we have to think about things like which system calls should incur what kind of challenges to guard what kind of resources. And in particular, we have to think about the difference between local and remote calls. And we maintain a permissions cache so that if you've accessed a file recently, you don't have to make the same proof again within the time frame. You can just use that permission which has been cached. So here's a quick example. When you go to create a file, so the first system call that happens is a getAttr, which is sort of a fuse equivalent of a stat. And what you need to do for that is prove that you can read tags about this file. Then the make node, which is basically the create step, happens. At this point, you have to prove that you have permission to both create a file and create the initial set of tags about it. Then another getAttr happens, and so this permission has already been cached, and we don't have to make another proof at that point. And then the new file is opened, and so we may have to prove the ability to read that file, write it, or both, depending on the circumstances for opening it. There are lots of other important design decisions that went into the system, which I don't have time to get into all of them in detail, but important ones include the ideas of how to support policy about tags. So we need to be able to express this tag-based policy in our logic. We need to be able to manage the various types of ways that people query tags and support policy about those queries. And we need to be able to combine tag permissions over sets of different tags that people have. We also put a lot of thought into how to support negative policies. So for example, the idea that you don't want to share your weird photos. And handling negative policies is sort of an ongoing problem in access control. There are a lot of different approaches, and we talk in the paper about what we decided to do. And we also have to deal with managing distributed sources of authority. So understanding whose permission do you really need to get access to some piece of content. Does it depend on where it lives in the network, where copies of it are, things like that. Just a couple of highlights of our implementation. So this is written as 15,000 lines of Java code on top of Fuse. Our access control logic is an intuitionistic first-order logic, which the reference monitor is charged with understanding the rules of the logic to validate proofs. And each user agent has access to a little homemade theorem prover, which is lightly optimized for the scenarios that we target to enable these users to make proofs and get access to data. So next I'll talk a little bit about our case studies. So our approach to evaluation here is something that I'm calling case studies. In an ideal world, we would love to deploy this system and have people use it for a while and see how it works. But this is pretty hard to do for a variety of reasons, not least because there wasn't really a great existing system with wide distribution that we were able to just bolt this idea sort of onto. So instead, what we do is we create a set of detailed policies drawn directly from our user studies. And we set these policies up to be representative of a broad set of the common cases that we saw when we spoke to lots of people. And by basically writing down these policies in our logic and expressing them in our system, we can demonstrate that our policy language is sufficiently expressive to capture these needs. And basically, by starting from these detailed policies, we create a rich set of sample file access traces. So the information in these traces, which is from the point of view of the content owner, is highly accurate. So things like policies, tags, content, this comes directly from our user studies. On the other hand, our studies didn't deal directly with the perspective of the people accessing the content. And so the access patterns are simulated, drawn from information from the HCI literature. And we're actually currently in the process of putting together another user study, which is going to look at things more from the perspective of the people accessing the content to help us improve these traces and make them even more accurate. So just two examples of what I mean by our case studies. The first example is Suzy. So this is a study that deals only with photos. Suzy exemplifies what we call a default share mentality, which is the idea of wanting to share almost everything and only restrict those things which are really important to keep private. So she has exceptions of not sharing things that are highly personal, things that involve kids, for example. This case study involves 60 users, 2,300 files, and 68 policy credentials. And when we run it, it generates about 47,000 proofs and 212,000 relevant system calls. Another example is Heather and Matt. This, in contrast to Suzy, is a default protect case. So Heather and Matt want to keep all of their content close, except things they particularly want to share. This one uses a broader set of content than just photos, and as a result, it includes both read and write permissions. And this one also includes 60 users. It's about 3,100 files and 101 policy credentials. And this one, when we run it, generates about 40,000 proofs and 267,000 relevant system calls. So the results of our evaluation. So first I'll talk about our experimental setup. So our goal here is to measure the latency of these system calls. We know from the HCI literature that operations that take less than 100 milliseconds are invisible to users. But we know, of course, that there are several system calls that go into any user visible operation. So we want to make sure that all of our system calls fall well underneath that limit. And when we run each case study, we set it up as follows. We create the initial set of files and tags and policies. And then each of the users in the study takes a series of weighted random actions, simulating the types of actions that they might want to take and files and content they might want to access. And then at the end, we have them take a set of known invalid actions so that we can understand the performance of the system when people try to access things that they are forbidden to access. And for comparison, we do a set of runs with the access control turned off. So basically, what happens here is just every time there's an access, it succeeds immediately with no need for proving or computation of any kind. And the idea here is to provide us with a control case so we can measure the overhead that the access control adds to the system. So we run our tests on a set of devices, which are actually Linux desktops, and they're connected via a local gigabit Ethernet switch, and we do 10 runs of each case study. So I'll show you the results for all of the system calls. Before I do that, just a quick refresher on how to read a box plot, just in case anybody hasn't seen one for a while. So the fat line in the middle is the median, and then the edges of the box represent the first and third quartiles of the distribution of latencies for the system call. And then the whiskers in this case represent up to 1.5 times the interquartile range, which is basically the distance between the first and third quartile. So it's the biggest data that falls within, or the smallest that falls within that range. And so in this case, we're looking at the make node system call, and it has a median of a little less than 20 milliseconds. So the results for all of our system calls show that most of them are well within this 100 millisecond limit that I'm talking about. And in particular, getAttr, which has to be very fast because it's implicated at least once and sometimes twice in every basically user operation, is particularly fast down there at between 1 and 2 milliseconds. So the exception to this is readdir, which takes a little bit longer. This happens for a variety of reasons, which we have a lot of ideas about how we can go back and improve this going forwards. So next, let's take a look at the overhead. So the white boxes are what was there before, which is the syscall latencies with the access control turned on. The blue boxes are with the access control turned off. And so we can see from this that the overhead of the access control itself is actually a very small part of the overall latency. And in particular, it's well under 5% for most of the system calls. And with readdir, again, being a slight exception, but the overhead still being quite low. And in addition to that, because proof generation is actually what you would consider to be the most important bottleneck for a system like this, we wanted to go back and understand how long it takes to make proofs and how this contributes to the overall performance. So we know that we want proving to be fast for the common case. And in our system, the most common case is people accessing their own content, and also devices making proofs in order to access remote content from one device to another. And so what you can see in this graph is that that's definitely true. The first column over there is file owners or primary users who can make proofs for their content in about 1 millisecond. And the devices are also pretty fast in about 2 to 3 milliseconds. We also did a lot of microbenchmarks to understand how proving time is affected by changes in the types of policy and content that exist in the system. So I don't have time to show all of these, but they're in the paper, and some of them are also on my poster, so you can come talk to me about them later. And we also looked at how long it takes to conclude that no proof can be made if you're trying to access something to which you don't have permission. And we found that these, for the most part, are pretty fast, with a median around 9 milliseconds, but they do have a bit of a long tail. So just to sum up, what we've done is develop a more usable design for file system access control. It rests on top of tag-based policy specification, as well as logic-based policy enforcement. And based on this design, we've generated a prototype distributed file system that implements these principles. To evaluate this system, we've developed a set of realistic case studies that include policy benchmarks and detailed file access traces that can be used for evaluation and potentially be applied to other systems in this space. And we found that even though we've done very little so far in the way of trying to optimize performance on this system, our performance is acceptable for the interactive use cases that we're targeting. Thanks.
Hi, I'm Tiratat from the University of Chicago.
Hi.
I have a question about the tag. So if I want to read something, I need to have access to read tag permission. Am I correct?
So it depends on the policy. So it might be the case that I would grant you access to one particular file, and so you wouldn't need to know any tags about it. But in the common case, you would expect to have policies like all the photos from my birthday party, and so then you would need access to find out which photos are tagged with birthday party in that case. So you don't need to be able to read all of the tags for a specific file, but you just need the ones that directly apply to letting you then exercise your access to the file itself.
Okay, thank you.
Sure.
Hi, this is Yuan from University of California, Santa Cruz. So what kind of algorithm did you use for the cryptographic signature, and how much overhead does it cost?
Right, so we're just using off-the-shelf crypto coming from Java, and it's it is adding some overhead, but it's not too much.
Okay, so the reason I'm wondering this is because I imagine for every access call, the signature has to be verified some way, right?
Yes. So when the proof gets generated and then gets handed to the reference monitor, who actually then verifies that the proof is correct, and that has two steps. The first step is verifying that the logical inferences in the proof are correct, and the second step is verifying that each credential used in the proof is properly signed and has not yet expired. But it turns out that verification is actually very fast compared to the proof generation itself. It's much faster.
But the sender has to sign the request, right? That is not only a verification but also a generation.
Right. So at the time when you go to make an access, your agent will sign something for you that says that you're the person who's trying to make the access. But that's also very fast compared to actually finding the proof. That's just signing one short statement in the logic. So
Okay,
it's
thanks. I'm sorry, I have another question.
Sure.
So you mentioned, maybe I missed this. So it's a distributed file system. It's a prototype, right? So what kind of the underlying distributed file system is this?
right. So it's just so we built it ourselves. So it's not too fancy, but it just allows you to access content which is stored on any of the other devices that are participating in the system. So
This sounds like a good achievement by itself. Okay, got it. Thanks.
yeah.
Hello. So I have two quick questions.
Okay.
The first question I have is this intended to be a replacement for traditional POSIX, permissions, and ACLs?
So we think that something like this, yes, should replace those kinds of traditional things, because those don't offer the kind of flexibility that maps to the types of ideal policies that people are looking for, and so they don't map as well to the types of mental models that people have.
I understand. Oh, I forgot to introduce myself. I'm Michael McStroh from University of California, Santa Cruz.
Okay.
Our lab had a technical report a few years ago where we did a case study at LANL. And one of the things that we found out with LANL is that file sharing is a very difficult thing. A lot of users don't know how to do them. One more quick question is. Have you looked, with your research, have you been able to look into defaults? Because one issue that I foresee with this solution is that if users need to manually tag their files with the type of permissions that they want, the thing is that users tend to be lazy.
Sure.
Users tend to put everything in their home directory. They tend to, I don't know if I don't know how keen they would be on tagging everything. And so have you looked into like reasonable defaults that are good for ensuring reasonable permissions while encouraging users to set more fine-grained permissions if they want to share their data?
Sure. So I think there's maybe a couple of points to answering that question. So the first one is that certainly you can look for some kinds of reasonable defaults, but what we really found when talking to users is that what people are looking for just varies so spectacularly among people, not just in terms of what they do or don't want to share, but in terms of even just the way they conceive of the policy. So things like, does someone have to be present in order for this to be shared? That it's really hard to come up with defaults that sort of make sense to a broad set of people. That being said, I agree with you that asking people to sit down and tag all their content in this way is a big ask and is more than we expect users to be able to do. And so we think there's a couple of things here. The first thing is that more automated tagging is becoming more and more realistic with things like facial recognition or geotagging on photos, or things like the ability to extract keywords from documents. So hopefully the amount of manual tagging would be limited, and also things like you would want to add some interfaces that would help support users to remind them about the tags that they use most often or are most important to add to their content.
Yep.
So,
Thank you.
sure.
Just a very quick fundamental question.
Yes.
If you consider transitivity, oftentimes the biggest problem is you allow me to see your picture, but now I have your picture and it's out there.
Right. So, so there's a couple. I guess there's a couple of ways to think about this too. So the first thing is that, in some sense, this is a fundamental problem to access control, which is that if I give you the content and you're not trustworthy, at the end of the day, there's just nothing that you can do about it. You know, you can take a screen capture, you can take a picture of the screen with your mobile phone, right? So there's, at the end of the day, there's not a whole lot we can do about that. That being said, you can build stuff in these kinds of access control logics, which do things like limit redelegation. And so you can make it so that if I delegate policy to you, you don't have the power to delegate policy further. And so then if I still, you know, if you didn't take a screenshot of that content, you can't give somebody else the ability to go access it directly through the system. But of course, that can't prevent you from, you know, going outside of it in that way.
Thanks.
Sure.
Thank you. Let's thank Michelle.